Obviously, I've touched on phylogeny, but in this lecture, we'll talk more specifically about phylogenetics. Phylogeny is the evolutionary history of an organism or a group of related organisms. Phylogenies do not only provide information about evolutionary relationships among species, but they are also indispensable for understanding how evolution has occurred. By examining the distribution of traits among species in the context of their phylogenetic relationships, much can be learned about how and why evolution may have proceeded. In this way, phylogenetics is the basis of all comparable biology. I pointed out that homologous structures are those that are derived from the same body part in a common ancestor. Thus, the forelimb of a cetacean and of an equid are homologous because they are derived from the same bones in an ancestral vertebrate. By contrast, the wings of avians and those of odonatans are homoplastic structures because they are derived from different ancestral structures. Phylogenetic analysis can help determine whether structures are homologous or homoplastic. Recent fossil discoveries have revealed that many species of dinosaurs exhibited parental care. They incubated eggs, laid in nests, and took care of growing baby dinosaurs, many of which could not have fended for themselves. Some recent fossils show dinosaurs sitting on a nest in the same posture used by birds today. Initially, these discoveries were treated as remarkable and unexpected. Dinosaurs apparently had independently evolved behaviors similar to those of modern-day organisms. But examination of the phylogenetic position of dinosaurs indicates that, as I stated in the preceding lecture, they are most closely related to two living groups of animals, crocodiles and birds, both of which exhibit parental care. Therefore, parental care exhibited by crocodiles, dinosaurs, and birds did not evolve convergently from different ancestors that did not exhibit parental care. Rather, the behaviors are homologous, inherited by each of these groups from their common ancestor that cared for its young. In other cases, by contrast, phylogenetic analysis can indicate that similar traits have evolved independently in different clades. This convergent evolution from different ancestral sources indicates that such traits represented homoplasies. As one example, the fossil record reveals that extremely elongated canine teeth, saber teeth, occurred in several different groups of extinct carnivorous mammals. Although how these teeth were used is still debated, all saber-toothed carnivores had body proportions similar to those of cats, which suggests that these different types of carnivores all evolved into a similar predatory lifestyle. Examination of the saber-toothed character state in a phylogenetic context reveals that it most likely evolved independently at least 3 times. Saber teeth have evolved at least 3 times in mammals, once within marsupials, once in felines, and at least once in nimravids, a wholly extinct clade of large cat-like predators, and once in Barbara felines, another clade of saber-toothed forms with approximately 5 named degenera. Based on this evidence, combined with a phylogenetic analysis of the dentition of early nimravids, Barbara felids and felids, and a revision of Barbara felids' base crania, Morlow et al. 2003, demonstrated that the Barbara felinae carnivorans should be assigned to their own family. Barbara felidae, distinct from the Nimravidae and the Felidae. Barbara felidae are distinguished by the following: loss of maxillary P1, maxillary M2, mandibular P1 and mandibular M2, plesiomorphic tooth formula 3131, 3131. Apomorphic species additionally lose maxillary P2, mandibular P2. Canidae is one of the most diverse extant caniform clades with approximately 47 named genera, and one of the best fossil records dating from the Middle Eocene. Canines are the last and only extant canid radiation, with approximately 13 extant and 7 extinct genera, and the only ones to expand beyond North America. Canids are generally medium-sized and relatively omnivorous, with long rostra and a digitigrade stance. They are specialized for long-distance pursuit and are generally gregarious, forming packs with complex social systems. Felids are generally hypercarnivorous, with some of their distinguishing features including a short, blunt rostrum, retractable claws, well-developed carnassials, and a reduction of the post-carnassial dentition. Flynn and Wesley Hunt, 2005, recovered Nimravidae as basal feliforms, and Amphicyonidae, popularly known as bear dogs, as basal caniforms, weakly supported as the sister clade to crown clade caniforms. Among the majority rule consensus tree, the most used is the 50% majority rule consensus tree. In this tree, a branching pattern that occurs with a frequency of more than 50% is adopted. The number of steps, i.e. tree length, of 439 steps is indicative of character state changes. The consistency index measures the amount of homoplasia in a cladogram. It is calculated by counting the minimum number of changes in a dataset and dividing it by the actual number of changes needed for the cladogram. A low consistency index, less than 0.5, tends to indicate that much homoplasia has occurred. The retention index is also a measure of the amount of homoplasia, but also measures how well synapomorphies explain the tree. Most complex characters do not evolve fully formed in one step. Rather, they are often built up step by step in a series of evolutionary transitions. Phylogenetic analysis can help discover these evolutionary sequences. Avian theropods, with their wings, pneumatic bones, and furcula, are exquisitely adapted flying machines. Fossil discoveries in recent years now allow us to reconstruct the evolution of these features. When the fossils are arranged phylogenetically, it becomes clear that the features characterizing living birds did not evolve simultaneously. The figure shows how the features important to flight evolved sequentially, probably over a long period of time in the ancestors of modern birds. One important finding often revealed by studies of the evolution of complex characters is that the initial stages of a character evolved as an adaptation to some environmental selection pressure, different from that for which the character is currently adapted. Examination of the figure reveals that long leg feathers evolved deep in the theropod phylogeny, in animals with forearms clearly not modified for flight. Therefore, the long leg feathers must have evolved for some other reason, perhaps serving as insulation or decoration. Through time, these structures have become modified to the extent that modern feathers produce excellent aerodynamic performance. Understanding the causes of patterns of biological diversity observed today can be difficult because a single pattern often could have resulted from several different processes. In many cases, scientists can use phylogenies to distinguish between competing hypotheses. Why do some types of animals exhibit more species richness, a greater number of species per clade than others? Phylogenetic analysis can be used both to suggest and to test hypotheses about such differences. Beetles, order Coelurostra, are the most diverse group of animals. Approximately 60% of all animal species are insects, and approximately 80% of all insect species are beetles. Among beetles, families that are herbivorous are particularly species-rich. Examination of the phylogeny provides insight into beetle evolutionary diversification. Among the Phytophaga, the clade which contains most herbivorous beetle species, the deepest branches belong to beetle families that specialize on conifers. This finding agrees with the fossil record because conifers were among the earliest seed plants group to evolve. By contrast, the flowering plants, angiosperms, evolved more recently in the Cretaceous, and beetle families specializing on them have shorter evolutionary branches, indicating their more recent evolutionary appearance. This correspondence between phylogenetic position and timing of plant origins suggests that beetles have been remarkably conservative in their diet. The family Mnemonichidae, for example, appears to have remained specialized on conifers since the beginning of the Jurassic, approximately 210 million years ago. The phylogenetic perspective suggests factors that may be responsible for this incredible diversity of beetles. The phylogeny for the Phytophaga indicates that it is not the evolution of herbivory itself that is linked to great species richness. Rather, specialization on angiosperms seems to have been a prerequisite for great species diversification. Specialization on angiosperms appears to have arisen 5 times independently within herbivorous beetles. In each case, the angiosperm specializing clade is substantially more species-rich than the clade to which it is most closely related, termed a sister clade, and which specializes on some other type of plant. Why specialization on angiosperms has led to great species diversity is not yet clear and is the focus of much current research. One possibility is that this diversity is linked to the great species richness of angiosperms themselves. With more than 250,000 species of angiosperms, beetle clades specializing on them may have had a multitude of opportunities to adapt to feed on different species, thus promoting divergence and speciation. Homologous traits are derived from the same ancestral character states, whereas homoplastic traits are not, even though they may have similar function. Phylogenetic analysis can help determine whether homology or homoplasia has occurred by correlating phylogenetic branching with known evolutionary events, and timing and cause of diversification can be inferred. Thank you very much. I hope you've enjoyed this thrilling lecture on phylogenetics specifically. I really look forward to seeing you in our following lecture.